Actually, I think I need a glass of water. Okay. So, again, you're starting to get familiar with the pattern, I think, right? We have a notion of judgment, which is a predicate, and which is either true or false. And then we have some rules that allow us to derive, those judgments that should be true. Here, these are they're called hoare rules. And we have basically one rule per syntactic syntactic construct by statement type, and there are 5 statement types, so there are 5 rules. Except that there's a 6th rule at the end that's the consequence rule. So let's start with the 5 syntax-driven or syntactic rules. So for skip, it's easy. If you start in a state that satisfies P and you execute skip, you end up with a state that satisfies P because nothing has changed. Right? Assignment is a bit trickier because it kind of goes backwards, right? So you have the queue here, but the precondition is defined in terms of the postcondition. So it kind of goes right to left. So this says here, if the precondition held, I mean, if Q holds, but with A instead of X, so this means replace X by A in Q. So if the precondition held before, with, no, sorry, I shouldn't say the precondition, I should say Q. If Q held before with A, then it's going to hold afterwards with X, right? Another way to write it is like this, right? So maybe that's more readable. So you start with a condition that's true with A, then you say that X becomes, takes the value of A, and at that point, you're allowed to use X instead of A because they both have the same value. So that's fine. So you see, this is maybe the most intuitive way of looking at it. But this is another way to write exactly the same thing, right? Because this may also depend on X. And here this says whatever dependencies on X are replaced by dependencies on A. So we'll see examples. It's very counterintuitive. And every year there are students who say, oh, you should move that here, or you should exchange those two maybe, or both. And, the short answer is no. But we have, I mean, it really helps to see some examples here. Okay. We have the sequence rule, which actually looks very intuitive, I think. If you want to prove that if you start at P, you execute SS prime, you end up in Q, then, I mean, to prove that, you simply need to prove that there exists an intermediate predicate R, that exists between S and S prime. So your goal, in some sense, is to squeeze in an R here, and then to prove this tuple and this tuple. And this is what we have as premises, right? So P goes to R, and R goes to Q, right? So you can think of P, Q, and R as states, if you like, right? You start in state P, and then you end up in a state that R, and then from state R, you go to state Q. But actually what you have is not states, but sets of states, right? The predicate on states is isomorphic to a set of states. So, and this is this ability to reason about entire sets of states at the same time that makes hoare logic suitable for verification, right? You don't want to do testing. You don't want to do just one value at a time. You want to carry a whole, infinitely many values, ideally, infinitely many states with you, and prove the program correct for all of those in one swoop, right? And this is what hoare logic provides us with. So here you have if then else, where you have so a precondition here called I, and then you have two cases. You have the case where B is true and the case where B is false. And this is done here by adding B to the condition itself. So if you start in a state where I holds and as well as B, then you check that executing S leaves you in a state that satisfies Q, and if B is false, then you check that starting in a state where you know I and you know that B is false, executing S prime here leaves you in Q. And I must say, I don't know why I called this I here, so I think that really annoyed me. I should have called it P for uniformity. Right, okay. Now the while loop is usually the most difficult rule, I guess. So you start in a state where, you know, P is true. And then what happens is that you want, you're going to execute the body 0, 1, 2, 3, 4, 5, 6, 7 times. You don't know. So you're basically going to have something like this. Right? Basically, that's what happens. And at the end, you need, you know, a certain condition. But because you don't know exactly how many times you're going to iterate this whole thing, you need what we call an invariant. You need P to kind of repeat in some sense. So you want to have P here, P here, P here, and so on, P, and also P at the end. And that's the general spirit of the while loop, because I mean it might be iterated 100 times, and you don't want to specify 100 different predicates. You know, you just don't know ahead of time how many times it will be executed. So this is a spirit, except that when you execute S the first time, you know more than just P, right? Because this is while B, so it will execute S only if B is true, right? So we're going to, well, let's steal it from here. We're going to, we can assume every time it's going to run an S that it, you know, the condition was true. And we can also assume that once we're done, the condition must be false. So this is what we're trying to achieve ultimately, right? And this is what this rule achieves. So it says, you know, all the iterations in the middle are all identical, right? So you can all prove them like this. You can say start in a state where P and B, execute S, and just make sure that the invariant, you know, the thing that always reappears, holds. And then if B is true again, then you'll have P and B again, and you'll execute S, and you'll have P, and you continue with that loop until until B is false. And at that point, you exit the loop and you're in that state. So that's the justification for the intuitive justification for the while rule. So those were the 5 syntax-directed rule. And then the 6th rule is the consequence rule, which is about tweaking P and Q and transforming them into P prime and Q prime. So sometimes, you know, syntactically, you're going to have a mismatch. You're going to want to have a certain predicate in a certain place, and then but what you have is a bit different. Well, this lets you change it. So it says, if you have a, I mean, I'm going to read it top down. So if you have a tuple, well, you're always allowed to weaken the post condition or strengthen the precondition, right? So you can always restrict. So P prime here is more restrictive than P. So you're restricting the number of states that you're going to follow, and then obviously everything will still work like before. You know, in extreme case, you would strengthen it all the way to false, you know, which is the strongest predicate, whereas true is the weakest one. And then if you have false, then you've won, right? Any hoare tuple that starts with false is true. Just like any implication that has false on the left is true. And here you can weaken as well. So just like we did earlier, we had this output here, and I said, well, it's okay to just say that you have B equals 4, or even that you just have true. So I was weakening and weakening. Here, if I want to strengthen, I will say that B equals 7, right? That is stronger, or C, or any variable. Okay. So that's what the consequence rule is for, and it's the tricky rule of the hoare calculus, because everything else you can kind of propagate automatically, and then consequence is like, okay, when should I apply this rule? Although we'll see that there's a pretty good strategy for doing this, so even that rule is not so problematic in real life. Right. Yeah, I think there was a weird mismatch here, because it says in the while rule, I is called an invariant, but the I was in the if and not in the while. I think this is where it was supposed to be called I. So I'm going to investigate, and probably the version you look at will be fixed accordingly. So, but it's just a name, right? It could be called Z or Z if you prefer. Okay. And here's an example derivations. You can build the proof trees, and they're rather easy to build. You don't even have any side conditions on those to check. You just apply them mechanically. So that is kind of nice, right? But here you see this is a sequential composition, right? So you have A equals 2. You assign to B, sorry. And then to verify it here, you remember there was an R that you needed to provide. And there was an R here as well. So we have to come up with the right R, but here it's pretty obvious. And also what I should mention is that I'm just applying the rules here, and I'm seeing the predicates in a kind of semantic fashion. So the assertion rule, yeah, I'm not sure syntactically. Oh no, it would work. Sorry, I forget everything I was saying. So here, when you apply the assertion rule, you see you have an A here and you have a B here, and this is exactly what happens. So, right. So this was the X before, and this was the A. Right. This was the variable X, and we have syntactically a perfect match. So these are perfectly valid trees. They're not cheating in any way, unlike what I was trying to say one minute ago. Here's another example where we use the consequence rule. So we start with x is greater than 10. We assign x to y, and then we have that y is greater than 0. And we weaken this to we using the consequence rule, we obtain we obtain. Oh no, wait a second, I'm reading it the wrong way around. So we start with this one here, which has x is greater than 5, and then we restrict the precondition, and we make the post condition less precise. Right. So we have less information at the end, which is a pity, and it's less useful because it's more restricted at the input, but apparently this is what we wanted to do. That's why we applied the consequence rule here. So these two formulas here, they don't really fit into the framework, so you could see them as side conditions, if you like, right? They're not hoare triples, is what I mean. They're just logical formulas. So they could have been viewed as side conditions, but traditionally in hoare logic, you just put them as premises, and you assume that they're in a different type of judgment. They're logical judgments, if you like. But that would have been equally correct in some sense to say if this and that holds as a side condition. In lean, it certainly will not matter which view we take. Okay, and then what we showed above was these standard rules, but there are also non-standard ones that we can derive from the standard ones. So there's an alternative skip, which is a combination of skip and the consequence rule, right? So, and the advantage of this one is that this is a so-called linear pattern. So all the variables are distinct. That means that we'll match anything, of the form blah, 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 skip, blah, blah, blah. So that's easier to handle for proving, and then we'll be left with this condition, right? So this will work even if there's no perfect syntactic match between P and Q, which is sometimes nice. And then same thing for assertions, for assignments. You you can also have a kind of a linear pattern here, and at the same time with same thing with while do. Right, and we give names with primes to distinguish them.